My name is Nick Dietrich. I am a first-year PhD student at the University of Colorado Boulder. And today I will be giving a talk on estimating neutral density of the thermosphere using data assimilation methods. Now, I have a background in aerospace engineering, and with this work, I'm really hoping to be able to bridge the gap between space situational awareness and physics-based modeling. Now, within satellite orbit determination, for low Earth satellites, the largest perturbation force that is causing the most error in our orbit predictions is satellite drag. And within satellite drag, the greatest source of uncertainty is within this neutral density term. Now, the neutral density state is pretty difficult to predict just because there's so much variability associated with the neutral density, as it varies so much from solar min to solar max, day and night, and especially during geomagnetic storms when a lot of energy is input into the thermosphere, which causes a large upheaval of neutral density, which really increases satellite drag and causes us to lose satellites. Now, currently, only empirical models are offer the best density forecasting, but what I'm hoping to do with my research is to use physics-based modeling coupled with data assimilation in order to provide more accurate forecasts for neutral density. And when I'm being able to estimate these neutral densities, I'm hoping to actually be able to map the neutral density errors that are estimated and try to map them to how orbit problems that orbit determination is experiencing, namely errors in satellite position, because they want to know exactly where a satellite will be within 24 and 48 and like 72 hours propagation. Now, this also poses a really big problem during geomagnetic storms when a lot of uncertainty within density exists. So I really hope using physics modeling and data assimilation provides that much better improved estimates for neutral density. Now, I'm having this approach for this problem because there really doesn't exist a global observing system for neutral density. Currently, the best neutral density data is just limited along the track of satellite orbits, since most neutral density is observed via accelerometers on board the spacecraft or from precise orbit determination. However, there do exist global observing systems for other systems, namely the ionosphere. And from this coupling between the two systems, we can try to infer states in the neutral density based on states from the ionosphere. Now, in order to determine to model this coupling between the thermosphere and ionosphere, general circulation model, TIEGCM, developed by NCAR, is used. And this model offers really good, a lot of advantages. Namely, it offers the coupling, it offers global states for the entire hemisphere, and as well allows to define time-dependent input changes so that storm time behavior can actually be modeled. And lastly, it's just a widely used model and very popularly used. Now, to accomplish data assimilation, an ensemble square filter is used, which is implemented by DART. And so the problem with trying to estimate the states for the thermosphere is that they are million by million states, and it's very difficult in order to invert over these million states without running into significant numerical issues. These are overcome by the ensemble part of the filter and the square root. Now, the square root it was able to ensure that the covariance remains positive definite, so that we don't run into numerical issues inverting. And conversely, the ensemble allows us to approximate the covariance and reduce the state from millions to have the covariance estimated by, say, 80 to 100 ensemble members. Now, so the reason that we can actually use this coupling for using ionospheric observations in order to infer states of the thermosphere can kind of be seen in this chart, where the background color is the neutral temperature from the thermosphere, and the white contours are electron density for the ionosphere. Now, along these red lines, we can see the cross correlation, negative cross correlation between the thermosphere and ionosphere. And because there exists this negative correlation between the two systems, if we have, say, a lot of observations of the ionosphere, we can expect that trying to update states using the ionosphere for the thermosphere can have a good impact and actually drive our model towards reality. Now, the global observing system that we are using to get information up for the ionosphere is COSMIC1 and 2, which uses radio occultation to get vertical profiles of the ionosphere. And COSMIC1 and 2 are able to really achieve this global observing system because there's already a global coverage of GPS satellites passing through the upper atmosphere with their radio signals. So it's able to capture these radio signals and really achieve a global coverage. And while COSMIC1 and 2 primarily use GPS satellite signals in order to complete these radio occultations, they can be extended to BeiDou, Galileo, GLONASS, GNSS systems, and really the potential to achieve a truly global observing system for ionosphere is really possible. So there's a lot of the power in this data set, I believe. Now, in order to compare how well our data sublimation is performing, CHAMP and SWARM will be providing truth data of neutral density, since they do provide high quality neutral density data. So for the actual experiment, a test case by Matsuo and Su was run for a test case at solar minimum in 2008 at some mild solar conditions. And for this experiment, COSMIC1 data was assimilated every hour and to a 90 member ensemble. And then the predicted neutral density was then compared against CHAMP neutral densities in order to assess how well the data sublimation was performing. So now, results from the experiment can be seen here with the O minus A being plotted, where the O observations are neutral density observations from CHAMP, and then the A is the analysis updated neutral densities that TIEGCM provided. Now, we'll note that only COSMIC1 data was assimilated, and CHAMP provided an independent observation source in order to verify how well the assimilation worked. And you can easily see that in the top graph, where COSMIC1 data was assimilated, we see much lower errors versus the control where no data assimilation was performed. Now in this chart, we can also see the results of CHAMP neutral densities over time. We can see the true true net neutral density in blue at the bottom. And as we can see, the red, where we assimilated COSMIC1 data, it becomes closer and closer to the true value, as well as we see that the RMS error ratio between with and without data assimilation is reducing over time. Now, while it does improve, there still does exist this bias between what TIEGCM is estimating the state to be and what CHAMP is saying the true data. And this bias is kind of hopefully to be my work in the future in order to try to reduce it and to get better estimates. Now, what I'm trying to do to extend this work is to find ways to actually map how these neutral density errors are connected to errors in satellite positioning. Now, I'm achieving this by just taking CHAMP's orbit and then propagating it through the neutral density fields that TIEGCM provides. And I'm just doing this via these three simple dynamics for two-body, J2, perturbations from the Earth, and most importantly, the satellite drag. And then once I get this final position after, say, 24 hours, I'm rotating into this frame, since it's a much easier frame to understand the errors, as most of the satellite drag force is going to be occurring within this direction. Now, after 24 hours, we can see the comparison between with and without data assimilation. And we do see a significantly reduced error in position when we assimilate COSMIC1 data, which really matches what the results are as the neutral density from TIEGCM estimates were driven closer to Champ's true states. Now, it still didn't perform as well as if just no satellite drag was included. And really, I attribute most of this due to still like the bias that exists between what is being estimated for neutral density versus what the true state is. And I'm really hoping, yeah, to be able to reduce this bias in the future. So for my current work, I'm trying to run similar experiments, however, with a couple of changes, notably using COSMIC2 data, since we are expecting that COSMIC2 data will hopefully be even improved from COSMIC1. And then while previous experiment results were verified against Champ, Swarm instead will be used, which will also, since there's a constellation of 3 Swarm satellites, even better analysis will be, verification will be able to be used. And also I'll note that this storm time is also this conditions are a bit quieter for solar, and an 80 member ensemble was used. Now, for this experiment, still a lot of work is needed to be done. Currently, there is too large of a gap between the observations that COSMIC2 is providing and the a priori states that exist within TIEGCM. And so these are plots of the difference for electron density. And as you can see, there are pretty large fractional errors. And now these fractional errors are really too large in order for when COSMIC2 data is being assimilated, the filter isn't trusting enough these observations in order to drive TIEGCM states more towards the observations. So a lot of work is going to have to be done to reduce this bias and tune the filters. Now, this brings me to my future work. As I just mentioned, tuning the filter and adjusting for this bias are really the 2 main components that I hope to work towards in the future. I hope to tune the filter better by inflating the covariance so that this ensemble spread of TIEGCM states don't become too compressed to never trust COSMIC2 observations. And as well, I hope to try to adjust the TIEGCM bias, as you saw with the large difference between neutral densities. And this is hoping to be, hopefully can be addressed by adjusting the forcings that TIEGCM is input from the ionosphere and solar, and then also to eddy diffusion. Now, once this experiment is successfully running, I can then use swarm data in a similar fashion that was done for Champ and compare against how well the neutral density was being estimated. And as well, I can hope to use a Monte Carlo simulation to propagate swarm satellites through the neutral density field that's estimated, and hope to gain a better understanding of how these specific neutral density errors are actually mapping to errors in satellite position. And finally, I'm hoping to actually look during storm cases where I'm really hoping to see the most benefit in modeling these storms. In conclusion, COSMIC1 data was successfully assimilated into TIEGCM and showed improvement in estimating neutral density. And these neutral density estimates actually did correlate to better orbit prediction errors. Now, still a lot of work has to be done to remove this bias and adjust the model. But that's really all I have for you today. Thank you so much for listening. You can contact me at this email if you have any questions or comments. And yeah, thanks for listening.